Okay, let me give you the connection between the least squares estimate of a regression line and a so-called maximum likelihood estimation of the parameters of the line. I introduced the general idea of maximum likelihood earlier on, so I'll not define this again, but actually I will show to you that the least squares criterion that most people do when they do regression, in fact, is a maximum likelihood estimate also. And that is not that difficult to see. Now, for maximum likelihood approach of regression, you could say, we would need to specify the model. The model would say, as the usual regression model says, here's one way of putting it, that the mean of the individual y's are given by the regression line, and the variance is sigma squared, and the distribution is the normal. This is just the usual regression model as expressed also earlier on. Here I put it this way. Now, the general principle of likelihood theory would then try to express the unknown parameters of the model, which are three things: the slope, the intercept, and the underlying variability. These are the underlying unknown parameters of the model. We could express that by the normal density function. The likelihood function becomes the product of each normal density, inserting the unknowns, e to 1 over 2 sigma squared, yi, and then the mean would be alpha minus beta xi squared. This is the normal density function used for the likelihood function. And then the log likelihood function, which is usually found instead, because of simplicity, becomes the sum of y equal 1 up to n of, we should take these terms first. It would be minus log square root 2 pi sigma, that's the first term, and then plus the log would then cancel out with the exponential, and we would have the sum I equal 1 to n, because we have the product that becomes the sum of all these terms, minus 1 over 2 sigma squared, and then yi minus alpha minus beta xi squared. This would be the likelihood function. Then the point is, actually, we could just, in a way, for now, ignore the sigma. No matter what the sigma is, we can actually look at the fact that L alpha beta sigma is minimal we are going to maximize the likelihood. So the log likelihood is maximal when what? Well, when it comes to, with respect to alpha and beta, then this one doesn't really matter. Only this one matters. Only this one matters to minimize, to find an alpha and a beta, to maximize this one. Only this one matters, and the sigma cancels out, and there is a minus. And look at this term. So the likelihood function, the log likelihood function, is maximized if the sum of yi minus alpha minus beta xi squared is minimal. And now we're done, because here we have shown this is the least squares criterion. So assuming the normal distribution implies that maximum likelihood estimates of alpha and beta exactly are the least squares estimates of alpha and beta. So doing least squares corresponds to doing maximum likelihood based on normal assumption, actually. So there's a nice connection there between these two. When it comes to the sigma, the connection is a bit challenging with the dividing by n instead of n minus 2, but that was not my point here. My point was to focus on the alpha and beta estimation. Least squares is in fact maximum likelihood. Thank you.